equation 9.3 is in fact the precessional motion. Why do we have a precessional motion? That follows in the next direction, next discussion. Let us now think about the dynamics of a classical dipole in a magnetic field. The equation of motion is T L by dt equal to tau. The tau is the torque. So if we substitute the value of torque from equation 9.3 and the value of L from equation 9.6, we get this following equation 9.9. And here on one side I have handwritten this derivation. So the derivative of mu is equal to minus E over 2m into mu cross V. So the subscript on mu will be deleted henceforth for brevity, and since this leads to no confusion, so instead of showing the magnetic dipole moment as mu m, we will now show the magnetic dipole moment as mu. So this equation 9.9, in which the derivative of mu is equal to some constant into mu cross V. Now this is a typical equation of precessional motion. So this precessional motion is shown in figure 9.3, which states that the magnetic moment does not directly align with B or is opposite to B, but it is in a precessional motion around B. So that is very interesting, and we have derived this concept from this mathematical relation. So this precessional motion will have a certain frequency, and this is the frequency. Omega L is equal to EB over 2m. So this frequency is known as the Larmor frequency. So the dipole simply precesses around the direction of the field, always maintaining the same angle. For an electron at V is equal to 0. Weber per meter square and Larmor frequency is 10 gigahertz. So you can have an estimate that how large is this frequency with which we are having this precessional motion. So this statement concerning the Larmor precessional seems to cause some doubt on our earlier assumption that the dipole tends to align itself with the field. But in the precession, the dipole merely rotates around B without ever getting close to the direction of the field. The point is well taken. In a pure Larmor precession, no alignment takes place. But in practical situation, however, this precession is usually accompanied by numerous collisions. You know that the electrons are colliding in an atom, in a solid. So during these collisions, it will lose its energy, the energy will be dissipated and the motion will change. So when the motion changes, the angle with which these dipoles are having precessional motion, this angle will also change. So during which the dipole loses energy, as it does so, it gradually approaches the direction of B until eventually it lines up exactly with the field. So this is how the magnetic dipole can align with the field by losing its energy. always in recessional. This process of gradual magnetization is referred to as relaxation. So we call this the relaxation when the ultimately dipole aligns with the field. The potential energy of the dipole can also be written as E is equal to plus E over 2m into Lz into V. So here the magnetic field is taken along the z-axis, and the component of L along this field is to be taken here. So this is the equation which shows that the energy of the orbital electron depends upon n and L. N is the principal quantum number and L is the orbital quantum. Where we have used equation 9.6, here B is taken to be in the z direction and Lz is the z component of the momentum. So we recall that according to the quantum mechanics, the component Lz is quantized. You know this already. And this, the value of Lz is always equal to a kinetic quantum number ml into h cut. So ml is an integer which takes the values minus l plus 1 etc. to l minus 1 to n. Changes from the magnetic quantum number ml can have values from minus l to plus l. You know this. This is the famous result from atomic physics, and where L is the orbital quantum number for the angular momentum of the electron. So this equation 9.11, may then be written as E is equal to E h cut over 2m into B ml. The ratio mu B here, E h cut over 2m, which is a constant. This constant is called the magneton, and its numerical value is 9.3 into 10 to the power minus 24 joules meter square per Weber. So we may therefore write equation 9.12 as E is equal to mu V into B into L. Writing the Bohr magneton as mu B. Magnetic moment will be written as magnetic dipole moment will be written as mu, and mu B shows the Bohr magneton. So as ml takes its values various allowed values, the energy also takes its approximate values in the presence of the magnetic field. For example, for L is equal to 1, ml will take the values minus 1, 0 and 1, and therefore there will be 3 energy states with L is equal to minus 1 and 0 and 1, and these 3 states are shown in figure 9.4. Now mind you, this splitting of the energy states into 3 states only occurs when the magnetic field is applied. When there is no magnetic field, that is B is equal to 0, we have only one state. So this splitting of an atomic level by a magnetic field, you know, this is the famous Zeeman effect. And for L is equal to 1, The splitting of an atomic level by the magnetic field in the manner just described is known as Zeeman splitting. So the interval between any two adjacent levels is the same and is given by delta E is equal to mu B into B. Note that the lowest level ML is equal to -1 corresponds to the orientation in which L is opposite to B, and hence mu is parallel to B, in agreement with the classical picture. So this quantum mechanical picture tends to the classical picture ultimately using the correspondence principle. Similarly, the highest level ML is equal to 1 corresponds to the orientation in which mu is opposite to the field. Okay, so that was the Zeeman splitting due to the orbital motion of electron. We have this similar Zeeman splitting in the spin motion, but because spin can have only two values, plus half and minus half as the quantum number, so the Zeeman energy calculated on the same lines using equation 9.12 is given by E is equal to 2 mu B into B into MS, where the factor 2 arises from the fact that the spin gyromagnetic ratio is twice the classical value. Since the spin quantum number can have two values, S is equal to half and MS is equal to half and MS is equal to minus half, the corresponding Zeeman splitting composed of only two lines is shown here. So the differences in energy between the two levels is now delta is equal to 2 mu B into B, which is double the orbital separation. So for the spin motion, we will have splitting in two energy levels, whereas in orbital motion, the splitting depends on the orbital quantum number L. If L is 3 there, then ML will change from -3, -2, -1, 0, 1, 2, 3. So that there should be 7 levels in the splitting, Zeeman splitting. But the splitting in the spin motion gives us only 2 levels. Let me stop here. You must go through these pages. I have explained some of the underlying principles, and you must go through these pages and come up next time with the understanding of these basic concepts of magnetism. Okay, thank you very much.